you can see, I think you can see my screen now. Yes?
Yes.
Yes.
Okay, thank you. Thank you, everyone. Hello. Thank you, Julian, for your kind presentation. Yes. As he said, my name is João Carvalho and I'm a PhD student. In fact, I started my PhD in January. I'll be bringing to you a theme that is quite related to my PhD, which is we'll be talking about polysaccharide-based bioinks for 3D bioprinting applications. So, words, many of those concepts and many of those themes to the table. So I won't dive too deep on some of them. So it won't be a repetition of what has already been said. But so the presentation will begin with a brief introduction, a brief overview about 3D bioprinting. But then we will focus on bioinks. What are bioinks? Why are they important? And why are they the key to the success of this 3D bioprinting process? We will specifically focus on polysaccharide-based bioinks. We are at EPNOE, and so polysaccharides are very interesting and very important for us. We will make a brief state of the art, and then we will talk about our work at Biopol for fun. What are we doing and why are we doing it? In this area of 3D bioprinting, and then we will finish with a brief conclusion. And so, as I was saying, 3D bioprinting, I'm sure you've all heard of 3D printing, about the layer by layer deposition of certain materials to create a new object. In this case, when we talk about 3D bioprinting, most of the times we talk about the layer by layer deposition of bioinks. This deposition is controlled by a computer, and so how do we do this? We use computer software, and so this is a process, a computer-aided process to deposit these bioinks. We will talk in greater detail about them soon. But we have the layer by layer deposition of these bioinks in order to create a new tissue or a new organ or a new construct. And so, as I was saying, this 3D bioprinting will create three-dimensional functional living tissues, and with tunable characteristics in terms of size, in terms of shape, and in terms of porosity. But why do we want it? Why is 3D bioprinting important? Why are we talking so much about 3D bioprinting? Well, of course, our golden standard, what we would love to do would be the organ printing, the possibility of creating an organ from scratch. This would be, of course, the desirable end of all of this. But right now we are still making our steps towards it. And right now what we are able to do is we are able to create some tissues for tissue grafting. We are able to create some tissue models for in vitro testing. And of course, there's also been an increasing interest in using 3D bioprinting for medical devices and medical implants in order to circumvent some of their limitations. And so it's very important that we understand that the bioprinting process is way more than just the printing of the bioink. It can be divided in three major steps: pre-bioprinting, the bioprinting process itself, and the post-bioprinting. When we talk about pre-bioprinting, what we mean is that we need a detailed knowledge of the original tissue, and this will be vital for the whole bioprinting process. What we mean by this is that we need to know what we want to build, or what organ or tissue we are trying to mimic. And for this, we use imaging techniques, for example, the MRI, to understand the structure of the original or the living tissue itself. Then it's very important that we carefully plan the structure that we are going to build, that we create a 3D model or a design in a computer software of the tissue or the organ that we want to build next. Of course, this design will have to mix all the properties that we talked before, and will have to be optimized in order to optimize the features of the final tissue. When we talk about the bioprinting process itself, and I know this is what matters the most to most people, this stage is very important, of course, and also includes something that is very forgotten or not talked about, which includes the preparation of the bioink or the choosing of the bioink and the choice of an appropriate or a suitable bioprinting technique. As you may see, the success of the whole bioprinting procedure will depend on the choice of an appropriate bioink and an appropriate bioprinting technique. An appropriate bioink for what we want to build, and an important bioprinting technique that considers what bioink we are using. I won't dive too deep on the different bioprinting techniques. I just want you to know that we have different ways to bioprint. One of them, and the most common one, is the extrusion-based bioprinting, in which we have the pneumatic or a piston causing the pressure and causing the bioink to leave through the nozzle, as you can see here. We also have the inkjet-based bioprinting, which is inspired by the inkjets of our printers and uses a heater or a piezoelectric actuator to make tiny bubbles, or yes, I think I can say tiny bubbles of ink that are extruded. But we also have laser-assisted techniques available, which use pulsed lasers to achieve more or less the same effect. So, it's very important to consider also a post-bioprinting stage in which the novel tissue will have to maturate in a bioreactor and will eventually have its features tested in vitro. The new tissue after this process and after this study may be implanted or even applied for its designed application. For example, if we created an in vitro research model, it may then be used for that. But so I've been talking about bioinks a lot. I've been saying the word bioink a lot. But what is a bioink and why is it important for 3D bioprinting? Well, as a general definition, we may say that the bioinks are the biomaterials or the materials that contain living cells that are deposited by the bioprinter in a layer-by-layer fashion. I want to make very clear that it's vital that the bioinks include living cells, of course. So the living cells are our major ingredients, but there are some bioinks that include only living cells, but most of them also include another kind of biomaterial. Professor João has talked a lot about hydrogels, but there's also, and hydrogels are very used for this, but also the cellular matrix is very commonly used together with living cells in order to create a bioink. But the bioinks are not all the same. There are different kinds of bioinks, and most of the times we divide them by scaffold-based or scaffold-free bioinks. When we talk about scaffold-based bioinks, we base this on the idea of the cells being in a surface or in a matrix. Where we have hydrogels, as we already talked about. We have microcarriers, and I would like you to take a good look at this because we will talk about them again later. Microcarriers are tiny particles. The cells will adhere to these particles, and so they will be adhering to a surface when they are printed. And then we have the extracellular matrix, in this case, decellularized extracellular matrix, which is also a very nice matrix for our cells. This is the most investigated type of bioink for 3D bioprinting applications. But we also have some scaffold-free bioinks. Sorry, let me just change the key. Yeah. We have scaffold-free bioinks. In this, we only have the cellular component. Most of the times we know there are tissue spheroids, which are spheres of agglomerated cells, tissue strands, which are the same, a close principle, but are in the shape of a strand, and we have cell pellets. These are increasingly explored since they have great biological performance, as you might understand, but they also have some limitations. And so we need to understand that bioinks are very important for the bioprinting process, and most importantly, An ideal bioink should provide the suitable mechanical features. Of course, it must have the suitable viscosity and cross-linking profile. It must be able to withstand the intensity of the bioprinting process itself. And of course, it must be able to withstand the forces that are naturally experienced by the original tissue. But also, and very importantly, they should have good biological performance, which means they should be biocompatible. They should ideally be biodegradable. They should have a high cell viability post bioprinting. The bioprinting process is often very aggressive for cells, and so it's very important that we keep a high cell viability during the process and after the process of bioprinting. And we also want our bioinks to have enhanced cell adhesion, growth and proliferation. And so, considering that we want this and that we want a good biological performance, the idea of using polysaccharides seems quite logical, right? So, when we talk about polysaccharide-based bioinks and the state of the art, as I was saying, it's very important that the bioink is made using biocompatible and biodegradable materials. And polysaccharides are a great option to achieve this. They have known biocompatibility and biodegradability. Most of them present very low immunogenicity, which means they do not trigger a very big immunological response. And most of the polysaccharides are able to form hydrogels and to mimic the components of the cellular matrix we've talked before, and therefore enhancing cell adhesion and cell viability. And so we cannot talk about 3D bioprinting and about polysaccharide-based bioinks without talking about alginate. Professor João has talked a bit about it. I won't dive too deep, but we all know that alginate is an anionic polysaccharide extracted from brown seaweed. And what's very interesting about alginate is its simple and fast dilation when we use its ability to cross-link with divalent cations and making this the most common material for bioink formulation. However, alginates often shows poor cell adhesion. Cells do not tend to adhere a lot to alginate materials, and they sometimes lack long-term stability. This may be circumvented by combination with other polymers, and that's something I really want to reinforce, which is that many bioinks use combinations of materials in order to have, as we spoke before, the good biological performance and the good mechanical features that we need. And something that's very dear to us at Biopol for Fun, and something that's very used to reinforce alginate-based bioinks is cellulose. Cellulose is also a polysaccharide. It's obtained from plants and some bacteria. I don't need to explain to you what cellulose is, but we all remember that it has remarkable mechanical properties and biocompatibility. It's commonly used, as I was saying, in the shape of nanocellulose, including bacterial nanocellulose, cellulose nanofibrils, and cellulose nanocrystals to reinforce bioinks from alginate or from other materials. In fact, I bring to you here a little example of a bioink obtained from alginate and cellulose nanofibrils, which was already used in a little of bioprinting, 3D bioprinting. And I wanted to talk to you a bit about chitosan too. It is a linear polysaccharide obtained through the acetylation of chitin. I don't want to delve too deep. It is poorly soluble in water, but it may be dissolved in pH below 6.2. And chitosan often shows weak mechanical properties. And so, as I've been repeating for a long time, it may be used with other materials in order to enhance its properties. You can see here on your right side an example of a bioink from chitosan. Other polysaccharides have been used in 3D printing techniques, including pectin, agarose, starch. And if you have some curiosity about this, you can search. There are many very interesting reviews on most of these polysaccharides. And so I wanted to talk a bit about our group and about what are we doing in this field, what do we dream to do, what have we achieved. So we are currently with a project Bioinks. It's about engineering bio-based nanofibers to develop nanostructured bioinks for 3D bioprinting, which means very simplified that we take our cells and we use natural fibers to create new bioinks. We are doing this, but we eventually are using or adding other biopolymers to the equation to make things more interesting, to change the things a bit. And so in terms of natural fibers or natural fibrils, we are using materials like nanocellulose, we've talked before, but also some proteic nanofibrils, for example, from lysozyme. And regarding the biopolymers, we like to use biopolymers like alginate, cellulose, pectin, but also gelatin and collagen. And so specifically, my PhD project aims to create new microcarrier-based bioinks from these nanofibrils. As I was saying, as I told you before, to be very to look closely at microcarriers. Microcarriers are little microparticles that will serve as a scaffold for cell adhesion for 3D bioprinting. And so here we want to create these microcarriers in one of three shapes, either as nanofibril spheres or as a nanofibril outer layer obtained by the layer deposition on a spherical template, or even as a nanofibril and biopolymer sphere. In this case, this is our first approach. This is the first one we are working on. We are using biopolymers together with nanofibrils in order to obtain these spheres for cell adhesion and for 3D bioprinting. And so, as I said to you, I started my PhD in January. I have the first preliminary results. They are very short, but I like them very much. I'm very proud of them. So we've already achieved the fibrillation of lysozyme. We started working with a protein first. We use certain conditions to make the fibrillation of lysozyme. But then we used this lysozyme to obtain microcarriers. As you see on the microscopy picture on the center, we achieved as Professor João said, the very easy spheres of alginate in calcium chloride. Everyone knows that. But then using the same technique, we used a combination of alginate and the fibrils. And as you can see, just from the optical microscopy, the spheres themselves are very different. The sizes are a bit different, but the spheres, we clearly see the presence of fibrils of fiber material in these microcarriers. And so what are we currently working on? We are working on reducing the size for 3D bioprinting endeavors. As you saw in the video Professor João showed, and in some of the schemes I showed here, the nozzle is quite narrow. And so if we have very big microcarriers, it will clog and it will jeopardize all the process. But also we are working on getting microcarriers from other polysaccharides, for example, from cellulose, fibrils, and some other things like that. And so in a conclusion, 3D bioprinting has very good potential for the creation of living tissues for fields like regenerative medicine and research. Of course, we all aim to see the day when we will be able to build an organ from scratch. It's still not today, but we hope it will happen. The bioinks deposited in this process are crucial for the success of the technique. A not suitable bioink will jeopardize all the process, all the steps of the process. And of course, polysaccharides are exceptional raw materials for this, for Bioink formulation, given their mechanical features and their biocompatibility. So I would like to thank, of course, our funding, our project, Bioinks and FCT, for my doctoral grant. But of course, I would like to thank you, EPNOE Webinar, for having me here and everyone who's listening. And last but not least, I would like to thank my supervisors and, of course, our group, Biopol for Fun, for everything. Thank you very much.
Thank you very much, João, for this very inspiring and very charismatic talk. So I'm very happy we could get you for this webinar here. As before, I would like to ask the audience to put your questions in the chat, and until we can receive the first questions, I would like to take the chance. And you were asking before, I mean, it's not your primary work now, as I've understood, but you were mentioning that those microcarriers can be also made by a template. And I was curious, which kind of template do you use? And is this template then removed? How you remove the template?
Yes, for now, I still haven't used a template to create the microcarriers. I know we can use, for example, silica templates or other materials. They might, depending on the material we choose, there are processes to remove them selectively. I have not used any of it yet, but I know they exist. I know it is possible. Even we can, if you use alginate or something, for example, we can collate the calcium ions using EDTA and creating, as Professor João showed in one of his slides, a kind of liquefied center. So what I want to say is there is the possibility of using these templates and removing them selectively after. For example, I know that silica templates can be removed selectively in the end. So, but I still haven't done it. I've just started and I still haven't explored much. Yes.
Okay, thank you very much, João. We also have now the first question here from Shunlin. He writes, thank you for the nice presentation. When you formulate your ink, did you use cell culture medium, and was alginate or nanocellulose stable in the formulation?
Yes, I still haven't formulated my bioink yet. I still haven't tested the bioink itself. As I showed you, I did the fibrillation of the protein and I started creating the microcarriers. I still haven't used them as a bioink, but I know from other works in our group that we will definitely use cell culture medium. And I know from other works in our group that the alginate and the fibrils we use, the fibrils are quite stable in the culture media from other works we've done, and the alginate seems to be stable too. So for now, we still haven't had that piece of trouble, but if we do, I'll make sure to show you all.
Thank you very much. Then Tina is asking a question. She writes, thank you, João, for the nice presentation. I wonder what is the resolution that is going to be required with printing organs with the bioinks. What I mean is, what are the smallest features to be printed?
Yes, that's quite an interesting question. Of course, we all still, in my case, I still haven't done the printing process itself. So I haven't tested how low or how high I can go in terms of resolution and in terms of detail we can achieve. I know some works in my group have already tested that and already have that data. I still don't, but I'm quite sure that we will have to be very detailed to create something as complex as an organ. Of course, organs are most of the times are not done by a single kind of cells and a single kind of structure, so they will be quite difficult to build as a whole, and they will for sure require different kinds of resolutions and different kinds of patterns and different kinds of bioprinting. So I'm sure it will be very difficult to achieve in the future. Right now, what we do when we want to test is print one of those little models. I think I had an image somewhere around here. When we do 3D bioprinting right now, most of the times what we do is we print something like this, you know, a defined structure. In this case, as you see, the squares have a size of about 1 millimeter, but I think smaller resolution has been achieved. These works are not done by us. I still don't know how my Bioinks will behave, but I'm hopeful I will have these results soon.
Thank you very much.
Thank you.
May I ask one follow-up question, because so far there is nothing in the chat. Because you mentioned now the organs, and I mean there is, I think, to my knowledge, there has been something implanted like bladders. Please correct me if not. But where exactly do lie the limitations to really currently print organs, and do you see any chance within the next decades to, for example, replace my liver?
Well, that's a tough question that requires a bit of prediction. I like to believe that we are moving at a very fast pace, and so we are already doing very good progress in tissues like cartilage and bone and skin, because of course we want to start with tissues that are easier to work or simpler to build, and some of these are very are simpler. For example, I've shown you a picture of a ear, which is mostly cartilage, and there have been successful printing of cartilage components. There has been some printing of some tissue, some skin grafts and things like that. I do believe we will see in the next, I mean, decades, I suppose, a very nice growing and increased printing on some of the simpler organs, or some of the simpler, none of them is simple, but some of the simpler models we can find. I can't assure you that we will be able to print a heart in 10 years or a liver, but I think we are making very good progress. There are many groups through the world working on different kinds of cells and different kinds of tissues, and very often these groups combine approaches and exchange approaches so that we can circumvent some of our problems. So I really do believe that we will have very nice breakthroughs in the next years. I can't assure you that we will have a liver for you, but I would like to say we will.
I hope I don't need one. Thank you very much, João, for your optimistic approach and for your presentation. I give the word over to Shunlin. Thank you.